Yeah, I'm really happy to be here, particularly since we're in this, jewel of modern architecture, which I'm a big fan of. So my name is Eirik Tsarpalis. I came from Greece to give you this presentation. And actually, before I start, I think I will skip directly into a demo. This was not the original plan of the talk, but new stuff has come up. It's just because of technical issues, I need to move this at the beginning, but it's pretty awesome. It's basically just using FSI to provision an MBrace cluster to Azure, basically. So I'm going to create a cluster that I will be calling nyc-fsharp. It's going to be based in West Europe. I'm going to use A3 cores, and the cluster size is going to be 4. I'm just going to run this. And basically I just provisioned a small cluster. It is going to take a few, if you're familiar with Azure, this is going to take a few minutes before it actually gets live. So I'll just leave it here and go back to the slides. So about me, I'm a mathematician by training. I actually moved into the world of development in general and F# and .NET in particular about 4 years ago. During which time I've been a research engineer at Nessos, which is a software company based in Athens, Greece. I've been doing a bit of open source work in the F#.NET world. You might know me through projects like FsPickler, Vagabond, which is I would say an assembly distributing library, and Argu, which is a sort of DSL for easily defining command line interfaces for F# programs, and you can find me on Twitter under this handle. So a few words about Nessos, which is my current employer. It's a software company based in Athens, Greece. We are Azure, F# and .NET experts, and we do quite a lot of open source work. I mean, the centerpiece, of course, is MBrace, which is being presented now. And apart from the projects I mentioned earlier, we've also been authors for libraries such as Link Optimizer, GPU Link, and Streams. And if you want to find more information about those, you can visit our organization at GitHub. So moving on to the actual topic of MBrace, let's talk about async. So how many of you guys have actually used async in F#? Can I see hands? Okay, so yeah, good percentage. So I would claim that F#'s most significant intellectual export is actually async. And this is, I guess this is because it actually takes something that has traditionally been very difficult, as in asynchronous programming, and it has actually made it very easy, making asynchronous code appearing as if it were defined in a really sequential way. And the success of async, as introduced in F#, is actually demonstrated by the fact that this has been actually incorporated into other languages as well, after F#. So C# 5.0 is a good example of this, and others are following suit as well. So the thing that MBrace does is that in the stead of async, it is introducing cloud-based Brace. And what cloud-based Brace is, if you're familiar with computation expressions, it is a computation expression for defining distributed computation and making it actually appear as if it were defined as sequential code. That's the very basic idea of it. And to give you an overview of what I'll be presenting for tonight's talk, I'll be spending some time on a high-level overview of the programming model. I will be giving you a few demos from my computer. I'll be offering some case studies that we have been doing with MBrace, and also give you an overview of the state of the project itself. So if you've used async, you might be familiar with this piece of code. This is basically an asynchronous workflow that asynchronously downloads the text from a bunch of HTTP files, and also it downloads them in parallel using this async.parallel primitive, which I guess you've seen is actually a primitive for async, which can be used for composing multiple workflows and have them execute in a fork join fashion. And this is actually done using the underlying .NET thread pool. And so This is the part that actually performs the asynchronous download in parallel. This is the actual callback that is being done while all the sizes have been computed, and this is what the callback does to reduce the initial results. And in this case, it just computes the total line count for all of the files that we have downloaded. So this is pretty familiar. So moving to the cloud equivalent of this thing, we have a very similar workflow. The main difference here is that async has been replaced with cloud. Again, we have a small nested helper function that takes something that we call a cloud file, which is basically just a path. We tell it to asynchronously read all lines from this cloud file and eventually return its length in an asynchronous fashion. And again, we parallelize over the inputs using cloud.parallel as opposed to async.parallel, and finally sum all the total computed sizes. So the main difference from the original example is that this actually performs the parallelism in a distributed fashion rather than a thread parallel fashion. So moving on to another example, I guess a second very common use of async is mailbox processor. So mailbox processor is a way in which you can actually use to define actors, in-memory actors in F#. You actually define the behavior of actors using async in tail recursive loops. In this case, I'm using a pattern that is not very common in mailbox processor usage, but it's the only one I could actually fit in a single slide. So, guys that are familiar with this, do bear with me. This is a tail recursive loop that is defined using async. This asynchronously dequeues messages from the provided inbox, and then increments a ref cell, which is also threaded in the body of the loop function. And finally, once a message has been received, it actually calls itself again with the updated counter. Then we initialize the counter, we start our mailbox processor in memory, we then post a few messages, and eventually we sort of verify that the effect of execution has actually taken place by evaluating the counter. Moving to MBrace, the story is pretty much the same. Again, we have a tail recursive loop function, which takes, again, 2 arguments. In this case, it takes something that is mysteriously called cloud atom instead of the ref cell. And it also takes an entity that is called a cloud queue of type int. And again, in the body, we asynchronously dequeue from our cloud queue. We update our counter using this mysterious function API, and then we return the body itself. And again here, the computation that is being done is the same. We allocate a new counter, we allocate a new queue, and finally, we fork the actor process inside our cluster and post a few messages to verify that the counter has completed. So you might actually ask me, what is this cloud atom of int? What is this cloud queue of int? And the answer here is that it can't be anything, really. These are actually abstract entities. It actually depends on the underlying cluster implementation, on what these actually mean under the hood. For example, if we were using Azure, the cloud atom in question would be basically just a row in table storage, and the queue would just be a queue in the service bus. But if you were in an in-memory cluster, then this would be a completely different implementation. So moving on, all this stuff is defined in a library/project that we call MBrace.core. I would call it async on steroids because it is essentially a natural extension of async. Like async, it is declarative, it is higher order, and it is also composable. And more importantly, it supports vendor-agnostic distributed computation. You can define a distributed workflow, and you can actually deploy this to differing runtime implementations. And of course, as you saw in the previous examples, we actually integrate storage and messaging abstractions for the distributed computation to take place. So I would call this a task parallel library for the cloud, essentially. And this is actually illustrated by this example, where I have, again, a cloud workflow in which I actually allocate an entity that is called a cloud cancellation token source, which, if you work with .NET, which I assume you have, you obviously are familiar with the cancellation token source. This is a distributed equivalent that has a global scope over the cluster, and it is also serializable. I'm then forking one process and have it do some work, pass it the cancellation token, and then I fork another process in the cluster, make it do another work, another piece of work, and again pass it the same cancellation token. And then wait until either of the two completes and return the first one that actually completes. And finally, if anything fails or basically just one finishes, I can just cancel my distributed cancellation token, and any outstanding computations can be completed. Another thing that is possible with the programming model of MBrace is that you can actually define user-level scheduling. This is a bit of an involved example, I would say. So, I mean, if it looks like a bit too information-packed, do bear with me. In this case, I want to define I want to define a parallel map function, which does what you would expect. It takes a function from T to S. It takes a set of inputs, a list of inputs, and it wants to map across the entire list, giving back the updated results. But in this case, I want to actually use my distributed capacity to sort of distribute work across my cluster. So in this case, this is a really pathological example of a cluster in which I have a really strong workstation and a really weak netbook. And I sort of anticipate that this has many cores, but this is like a single CPU thing with limited memory. So I do not really want to split my work into half and half and give half the work to the strong machine and then give the other half in the really weak CPU, which might not fit. So I just take the 2/3 of my initial inputs. I give the initial 2/3 to the strong machine, which is specified using this target parameter, and fork it. And then I send the remainder of the inputs to the weak laptop, which is the remaining 1/3 of the computation. I await until both complete, and then finally append the two results, receiving the computed list of the distributed map. Do you have any questions on this, by any chance? I would leave it as an exercise to the audience to find all the possible weaknesses that exist in this piece of code, because it's obviously crippled. But it's basically just a showcase of how I can actually write, ad hoc, separation of workloads across my cluster, given that I actually know the capacities and etc. Basically, this is a primitive that lets you query on the fly on how many workers I actually have on the cluster. And this returns an array, as you can see, of worker refs. And these are actually entities that can be used to represent workers in the cluster. And I can actually, target specific pieces of work to specific machines in my cluster. So to give you a recap of the two slides that I showed you before, MBrace Core is essentially a task parallel library for the cloud. It is possible to do user level, based on the programming model, scheduling or computation. And this actually makes it really strong because it serves as a building block for authoring distributed libraries of your own. There's actually an example that actually does this. This is our own implementation. We call it MBrace.flow. It is a distributed streaming library for MBrace. It's built entirely on top of MBrace.core. So in that sense, it is also runtime agnostic. It does not really require a specific underlying infrastructure in order to run. In terms of the API, it's very similar to Spark streaming. So we have a concept that is equivalent to RDBs, if you're familiar with that. And the actual execution model of the thing is based on Java 8 streams. I can actually direct you to this paper that was written by one of the persons actually sitting in the room, Angelos. He wrote a paper last year called Clash of the Lambdas that actually demonstrated the superior performance of Java 8 streams. So if you want, you can ask him afterwards. And we basically emulate this execution model. And to give you a sort of basic example of how this API works, we basically have a URI to an HTTP file that is considerably large. I think this is in the order of tens of gigabytes, so it's a dump from Wikipedia. We pass this to this function, which we call a producer. It takes any set of HTTP files and distributes the contents of the file across the cluster. And then you can perform all sorts of link-style operations on it. In this case, I collect on the line, which I split into words. Then I normalize my words. I filter so that I can exclude all the trivial words. Then I count by occurrence. And finally, sort by descending. And this actually is a really basic word count, distributed word count example, all done in 8 lines of code. So I mentioned before that MBrace.core and obviously MBrace.flow are runtime agnostic. So I guess you might be curious on what types of runtimes this thing can actually run at the moment. So we have 3 implementations already ready at the moment. One is MBrace.threadpool, obviously, which uses the thread pool, and in that respect, it is very similar to Async. It uses in-memory storage and obviously in-memory communication. We have MBrace.thespian, which is for on-premise standalone workers that are running on your infrastructure. It uses shared file system for the storage, and it uses it uses our own actor framework implementation, which is called Thespian, for the communication and actual coordination of the cluster. And finally, we have MBrace.azure, which utilizes Azure worker roles. It uses log storage and table storage for all the storage primitives, and the communication is done using Azure Service Bus. So I'm going to start, doing some actual demos. If you want to follow through, all the examples exist in this project. It's called MBrace.starterkit, and it has a whole lot of scripts that you can actually write, that you can actually run, and see some basic examples. So you can sort of find word count. You can find word count examples, image processing examples, k-means, Monte Carlo, stock trading, stuff like that. So it's a nice way to sort of familiarize yourself with the programming world. So I'm just going to switch into Visual Studio. So yeah, if you saw what I did at the beginning of the talk, I actually provisioned a cluster using my published settings. So I'll see if this has actually been set up by Azure. So if you cannot see this, I actually got back a value cluster, which is of type Azure cluster, and this is actually my basic client, which I can use to sort of send jobs using F-sharp interactive to sort of make sure that it actually worked. I evaluate cluster.show workers, and I'm getting some information. It gives me information on the workers that have been set up and running on Azure. Here are the host IDs, number of cores, CPU clock, percentage of memory that is being utilized, upload, download, etc. So in order to actually be able to deploy a computation to this, it's pretty simple actually. Just call cluster.run, and then just write cloud brace, return hello world. So it's producing a few outputs, it's downloading a few assemblies that are dependent on the code, and at some point I should be getting a result.
How is it capturing dependencies?
So it's using, so if you remember in my first slides, I showed a library called Vagabond. This is basically a .NET library that sort of uses reflection to traverse all the dependencies of any given object.
Okay.
And it sort of, groups them together for upload to, any cloud service that might be needing them.
So like Fusion, but like Fusion Log, like it knows how to do the bindings and stuff?
Yes.
Okay. Sweet.
So yeah, it just uploaded the computation, and basically there's no restrictions to this. You could just define a type, and it will still work. I should mention also that if you can see here, the servers are located in Ireland, I suppose. So there is a latency involved. And yeah, this is the result I got back, full type hello world. So the skeptic in the audience, might actually ask me, you're cheating us, you're just running the code locally, nothing is happening in the cloud, this is just smoke and mirrors. And so I guess I need to prove to you that this actually executes in the cloud. Could anybody sort of suggest a way that this could be done? Like how could I actually submit a computation in the cloud that sort of readily confirms that the computation has run on a different machine? Anyone?
Get local time?
Local time, yeah. I could do that. Yeah, that's good enough. So my local time is New York time, if I'm not mistaken. Yeah. But if I submit the computation, it's going to give me back 30 past 12, and the offset is 0. So this is actually local UTC time. And I guess, I think all Azure data centers run on UTC time by default. So yeah, that's the idea. Okay, moving on. Okay, I think I'll do another demo here. So assuming you're using async and you want to sort of actually verify that async.parallel is running using a multi-threaded execution, one way you can actually do this is calling async.parallel and give a bunch of computations that would return my next thread ID. So if I run this, you can, I guess you can trust me in the statement that these are different thread IDs. So I guess this is, I'll just call it array.distinct, I guess. So I guess this actually shows that this asynchronous computation has run on multiple threads. So I will take this example and do exactly the same thing to verify that the computation is distributed. But instead of returning the managed thread ID, I'm just going to return the machine name. I think I need to open system. obviously, instead of async.run synchronously, I just need to pass it to my cluster handle. Let it execute.
So it's pickling the actual expression and then uploading it.
Yes. So it actually serializes lambdas.
Is there any way to like sort of like precompile? Close with whatever would be the closest.
Precompile.
Meaning just sorry. Is there any way to like upload or reuse a previous computation that's uploaded?
Yes, I mean, you could obviously just, hash R any library that you are using, like, my local lib, .dll, and, just call the routines from that library. It is actually possible to.
Right. So you'd move it out of the expression.
Yeah.
Right.
I mean, obviously, it's a bit difficult when you want to sort of have repeating computations to have everything defined in the REPL, because it's something that's relatively volatile. You would want to keep everything in an assembly that you actually statically compile locally, and then just use the REPL to just upload the computation basically.
Does MBrace figure like on what's already been uploaded?
Yes.
Okay.
Yes. So if a dependency already exists in the blob storage, it will not upload it the second time. So yeah, I actually ran this and it gave me back 4 machines. So it actually utilized all the machines in my cluster, which is of size 4, basically. So let me move on to a less trivial example. That's interesting. I have no idea why this happened, but I think I fixed it. I'm sorry, this is just a merge that went wrong, I guess. Hopefully I'll be able to...
Missing a reference?
Sorry?
Is it missing a reference?
Like
It's missing like a modules.
I have no idea what's going on.
It's modular.
Indentation.
Oh, okay. Good. Wow. Okay, this is a merge that went really wrong. I might not be able to do the example, I think, but I'll try. Okay, seems to work. Cool. So, I mean, the module that I'm referencing defines some really basic stuff. So it defines a regular expression for splitting words, which is not obviously the best way to do things, but it's good enough for a demo, I guess. So it takes a line and splits it into word tokens. It normalizes words, and it also defines a set of sort of words that should not be included in the word count computation. So I have this isNoiseWord function, and I'm actually going to be using this when I write this example right now. Let's see if I ran this. For this demo, I'll be using the dataset that's found in textfiles.com. It's this really dated looking website, which has a whole bunch of public domain texts, which I've conveniently already uploaded to my blob storage account. So if you can't read this, it's got a bit of Aristotle, I think some Plato also. I think Shakespeare is in here. So I think this is about 150 megabytes worth of text files. So you wouldn't really call it big data in this case, but it's demo friendly, so I'm going for that. So I've written myself a few instructions here just to remember how I should be doing this. So I'm going to use Cloudflow to read text files by line, split into words, and cache to memory. So I'm just going to do that. So using the Cloudflow API, I'm going to call Cloudflow of cloud files by line. And this takes an enumeration of paths. If I actually try to evaluate this, it is going to return, if you can't read this, I'll use the tooltips, I think. That's even smaller. So it returns a Cloudflow of type string, and this is actually a distributed computation that I can actually tap into. So I can continue by, I guess, so this takes all the files and returns the contents of the files by line. So I guess the first order of business would be to actually split all the lines into words. So I'm going to call cloudflow.collect, and then I'm just going to take the line, and I'm going to use my word count module and call split to words. Then what should I do next? I should normalize. I should normalize all the words, calling cloudflow map, word count. That was something weird. Normalize. So now that I've normalized all my data, I can sort of count by themselves. So this is going to produce a frequency count. And since I've done with that, I can actually just sort by descending, because I want to just keep the top occurrences for this demo. So I write sort by descending, and obviously I need to sort by the frequency. And for reasons of performance, I also tell my workflow to just keep the top 100 and discard all the rest. This is something that's also done in Spark Streaming, I guess. And finally, okay, let me show you the type of this thing. If I just evaluate this, it's going to produce a Cloudflow of type string times int64, so it's word times frequency. So now I just need to materialize this, and I do this using a consumer of the stream. So I call Cloudflow to array, and if I actually evaluate this, it's going to produce a different type, and it's cloud of, well, string times frequency. So this actually, actually defines the distributed computation that will actually force this Cloudflow to occur across my cluster. And finally, since my return type is of type cloud, I can actually send it to the cluster for computation. So cluster dot, I'll call create process because I want it to be asynchronous. I'll name it word count proc, and just send it away, I guess. Now it's uploading quite a few dependencies. And I got back a word count proc. This doesn't mean that the computation is finished, obviously, but I actually have a handle that I can use to track the progress of the computation. So if I call word count proc show info, it's going to display some information which, so I have a bug here, I see. It's been running for -5 seconds. I've never seen this before.
Yeah.
And it has completed. It took, where's the execution then? It took 1 minute to complete, and cool. So it has actually completed, so I can just poke result, and I got my word count results. And obviously there's a bug here, but I actually forgot to normalize the noise words, so I actually have an empty string as the top occurrence. I could obviously just fix that, but it's a trivial alteration to my code. Obviously I can just easily resubmit the computation again and get the updated query. So yeah, I thought I saw a hand.
Can you show an example where you use like a
a data structure that's already in, like, I don't know how you would set up a data structure. Like, suppose you wanted to store a tree that could hold a terabyte worth of data. How would you do that?
A tree? You mean like a sharded tree that would be stored across the cluster?
Sure.
I could, but I can probably explain it to you offline, I guess. The idea is
the
that
Cloud Atom?
Cloud Atom, yeah, you could use Cloud Atom, but that's like a mutable entry. So in Azure, for example, it translates to a table storage entry. So depending on the actual size of each of the nodes of the tree, you would be constrained by the 64K limit. But we also have a cloud value, which I haven't showed in the slides. And this is like an immutable reference. And you can actually use that to define distributed trees, because you could actually go down the tree and at some point just point to specific references that can also be cached.
Do you have something that translates to a cloud translates to a blob storage?
Yeah, that's basically that's the cloud file. So the paths that I actually used for this computation, they are files in the blob store. So if we evaluate these, so these are files in the text files container in my blob storage account.
Got it.
Obviously, there are other wrappers on top of that. You can also define your own wrappers, like doing all the serialization and deserialization and caching. But as a primitive, we offer cloud value. That's the one that.
How would you do? Can you parameterize the cloud computation expression? Like how would you pass it parameters? Could you pass parameters with the computation expression as well?
Sure. I mean, you just define a
cluster run. No, I'm saying within cluster run, you pass the.
So in cluster run, it has to be a closed computation. So you would have to pass the parameters. Like if I would. So this is a stupid example, but
yeah.
This is a parametric cloud computation, I guess. Message.
Whatever, yeah.
So in the end, when you come to the point of actually running the computation, you would have to pass the parameter here. So.
Got it. Okay.
Yeah.
That's fine.
Cool.
What if you're working with an environment where you're mixing F# with C# and other .NET?
I have something to show later on in my talk about that.
Instead of like to array, could you use something that gives you back like a flow that like we talked about earlier with the flow library, and then they stream in?
What was that? Sorry.
And instead of turning it into an array, could you have like just kept it as a flow and had the results stream in?
Yes. So that's what the next demo is about.
Oh, okay, sorry.
Cool.
Jumping ahead.
So yeah, I'll move on to another example, which was actually really nicely done by Isaac Abraham. If you know Isaac Abraham, he's a really capable F# and Azure developer based in London, and he's also contributing to MBrace. If you follow his blog, he did this blog post a few weeks ago, and I basically just ripped off his code for my talk. He said it was okay, so there shouldn't be any problem. So in this case, I'm going to use type providers. And in particular, I'm going to use the CSV provider. So hopefully this will work. The input data in question in this case is the public data offered by the UK government on house pricing. So this specific file is in the order of 100 megabytes of CSV values that give price information for the entire UK in 2015. So this is basically just hosted on a web server by the UK government. I have already written this piece of code, which basically takes the URL. It is being passed to Cloudflow of HTTP file by line. And again, as done with of cloud file by line, it takes the data source, it splits it across the cluster, and you have a Cloudflow from that, a distributed workflow that acts on the data source. Yeah.
When you do by line, does each file, this is one file, so I have to break up each line and send
It could
to
be many
different
files. It could be, any number of files, basically.
But you could control it, and if you use, like, instead of by line, you could just get one file at a time to each worker.
Yes, but then the type of the Cloudflow, well, it would still be string, but each entry would just be a file, right?
It's a different problem than this one. Okay.
So again, this basically just reads the file across the cluster, and it gives you back each line entry. So again, in my map component, I use my type provider to parse the CSV. And then I call this primitive that's called Cloudflow.cache. And this basically, what it does is it takes the Cloudflow, it forces it, it computes it, and then caches it in memory across the cluster. So this will actually, when I run this computation, it will actually download all the data from the UK government across the cluster, perform the parsing, and just keep everything in memory. And this will return a type that we call persistent Cloudflow. And this is the MBrace equivalent of an RDV. So let me just zoom in again. Cool. Okay. Fortunately, I have to type directly now, but, So it's running, depending on whether the server of the UK government thinks I'm a bad guy. It might actually, disallow me. But actually, you can see here it has a bunch of counters. This actually gives you the total number of work items that are run for this specific computation, the number of ones that are completed, and the ones that are currently actively running. So I can see now that actually 4 machines are working on downloading the data. So let me just run this again. And it's completed. So it actually downloaded the data. It returned a persistent Cloudflow as this type, which was, of course, generated by the type provider. I mean, when I use it from IntelliSense, I'm going to see different things. So let me just get back my persistent Cloudflow. And this actually gives an interesting piece of input. So obviously the element type is the row from the CSV provider, and I'm getting some information on partitions. So this is partition number 0 assigned to this worker. It has this element count, partition size, storage level of caching, memory. This could have been disk, memory and disk, memory serialized, etc. And some additional metadata, I would say. So this is basically just a subtype of Cloudflow. So I can use it to chain it with future computations. But the future computations are going to be much faster because exactly this is already materialized in memory across the cluster. So, I mean, it's really easy to, extract data from this data set just by, taking cache prices. So, can you sort of suggest what I could find from this data set? Okay, I'll try to find the most expensive house. Sure. So max buy?
Not in London.
In London, okay.
Not in London.
Not in London, okay. House.
And not owned by the Queen?
Sorry? Town city, well, just to be on the safe side. Does that work? Max buy, house, and house dot price, right? And this actually has type cloud of fee. So if I run it, it's this one, okay? West Park. In a place called Surrey. Okay. And what's the price actually? Is that one?
Yeah.
15 million pounds. Anything else you would like to find out?
Can you know how many rooms is in this house?
Oh, I'm not sure.
Or you could have,
Oh, in that house.
or you could have how many houses are more than $10 million above him?
Okay. So, cash prices, cloud flow. What was that again? More than?
Yeah, 10 million pounds.
Oops. Okay.
That's it.
$36. Anything else?
Who listened?
Okay. So, so that's persistent cloud flows basically, and it's the same thing that you can actually do with Spark and arguments, but using Visual Studio, which is better. I think I'm done with demos. Maybe. Rick, how much time have we got?
Pretty much up to another hour if you want it, but
Ah. Okay. I'll definitely keep it within another 20 minutes, I guess. Okay, so I'm just going to show you one more thing. I think I mentioned that this version of Visual Studio that I'm running is Visual Studio 2015 Update 1. And can anybody tell me what's the biggest feature that we're waiting for in Visual Studio 15 Update 1?
Parsing React.js.
Perhaps. I'm not using JavaScript, so my favorite feature actually is, so I'm just going to open a different project for this. The nicest feature coming with Visual Studio 15 Update 1 is C# Interactive.
Oh.
And it's pretty cool actually. I mean, if you haven't seen it yet, it actually has embedded IntelliSense. So, I can, whatever.
Could you repeat what that feature was? Just couldn't hear it back here.
Oh, it's C# Interactive.
Oh,
So what you're seeing here is a REPL, pretty much in the style of F# Interactive, but using Roslyn, and you can actually interactively define computations using C#. So I guess the question here is, can you do MBrace with C# Interactive? I mean, given that so many people know C# rather than F#, and the answer is yeah, of course you can. I have this CSX file, which is basically the C# equivalent of FSX. Because it's a really early version, we actually just created this small proof of concept the other week, so it hasn't been released on NuGet yet. I'm actually not going to be using Azure for this demo, but this is just a just a minor annoyance. I'm going to use Thespian. And Thespian, if you remember from the slides, is just a local self-hosted cluster that we use. So we just put this again.
What do you guys use for messaging in Thespian?
We use Thespian, which is our homemade actor framework. Basically.
What is your underlying, how do
TCP.
you, just straight up?
Yeah.
Thespian does not run up on the cloud, it's just running locally.
Well, I mean, it's not, I wouldn't call it a production value implementation. It's basically, we basically use it for testing and for, educational purposes, I guess.
Do you intend to make it production? Is that something that you guys are thinking about?
That will depend on our customers, I would say. We're mostly focusing on Azure and AWS at the moment. We haven't really sort of put effort on, actually making this production ready. So obviously, what? Okay, sorry about that. I think I just need to build a solution. But see, it's got all the IntelliSense, nice syntax highlighting. I can actually zoom in and out, unlike F# Interactive. So, you know,
Brand new,
Microsoft
it
loves
has it.
C# and, you know, they spend quite a lot of effort of, you know, so yeah, I shouldn't be spending too much time on this. I mean, it's just a really simple demo. But I mean, let me just give you an overview of the code here. Let me just not run anything. So again, this is the same data set as I showed you before. It's the land registry.gov.uk. Here is a Cloudflow API, which is obviously the same, only adapted to sort of accommodate the C# dialect. So you have .select, .where, ordered by descending, and toArray. So again, it's exactly the same pattern. Again, you have the same cluster object. You can sort of, let me see if it works though. No, that did it. So this is a local cluster. That's why you actually see windows popping up on my machine. It's actually pretty convenient when you want to debug stuff. So yeah, I now have a cluster object, and you know, as before, I can sort of display all sorts of info. So yeah, I'll just run that, I guess. I think though that I'm just going to. Nah, never mind. I think it's going to take a bit of.
That's a big file.
It's a big file, and I'm actually downloading it
Yeah.
on my local machine. So I don't know. I'm just going to do something simpler, I guess. So Cloudflow. Oh no, I don't have IntelliSense here. So. But it works here. So it's CDP. So obviously there are a few issues. So I'm just going to call Cloudflow of array. So new int array 1, 2, 3, 4, 5. Is that good? Select x plus 1 to array, and just run it. Cluster run flow.
So you need print.
Yeah, sorry.
Welcome to you.
It's doing a bit of work, and it should complete at some point. Yeah. So yeah, basically you can use C# interactive to upload code, and I would expect to have this, in new releases of MBrace within the month. I guess. I mean, it's still something that is in early stages of development, but it actually works in principle. So yeah, moving back to the slides, I'm going to give you a few case studies on real stuff that we've actually run on the framework, and show you a few performance characteristics. So this is the word count example that I showed you. Again, so to give you an overview of what we did, again, the data source is textfiles.com, but obviously with a bigger set of inputs. We deployed an MBrace.azure cluster using 8 workers, which are quad-core, and I think 7 gigs of RAM, if I'm not mistaken. And we tested it using 4, 8, 16, 32, and 44 workers. And in this case, actually, the input size was scaled proportionally to cluster size. So, as we doubled the cluster size, we also doubled the data size. So the results that we got were these. And so this is sort of homogeneous, which is a good indication of scalability. So as inputs increased, as workers increased, the amount of time it actually took to complete the word count was the same, which was about 100 seconds for 16 cores and 684 megabytes, and moving on to 103 seconds using 176 cores and about 11 gigabytes of worth of text files.
How much of that is startup and how much of it is real work?
This is actually just a computation, so I have not included the download time. This is just this is using in-memory caching, so it has been cached as a persistent Cloudflow, and this is just the workflow that does the count by, the normalization, the count by, the order by, blah 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 blah. So, but there's, I mean, given that it's a word count, there's a big deal of communication going on, lots of shuffling of data across the stages of computation. So scalability is really something that needs to be proven in the case of word count. And yeah, obviously, I don't know if I mentioned this. This uses Cloudflow, so we could have written like a word count implementation that basically just used the MBrace primitives, like the PPM style computation. This uses Cloudflow, so obviously it can be optimized. Moving on, we have this example called KNet digit recognizer. The data source is the competition from Kaggle, which is this one, which is to classify handwritten digits using a supposedly famous data set. I'm not a machine learning guy, so I wouldn't know. In this case, I actually used an implementation in collaboration with Matthias Brande-Winder, who's a member of the F-sharp community based in San Francisco and also an expert in machine learning. He's written a book on it. So we used an implementation that uses a k-nearest neighbors algorithm, which basically just defines a distance across image bitmaps and sort of makes a classification based on the k-nearest neighbors based on the specific distance. Again, for this setup, I ran benchmarks on my local machine, which is a quad-core i7 CPU at 3.5 gigahertz, and also an MBrace.Azure cluster using A3 quad-core workers. And again, tested clusters were of size 4, 8, 16, and 32 worker nodes. In this case, the input size is actually constant across cluster sizes, so in order to actually see scalability, you should see a decrease in execution time. And these are the results. This is the number of minutes taken, and this is the number of cores. The bar on the left is essentially the time it took running on my local machine, which actually utilized the multi-core capacities of my machine. So it took about 15 minutes. It took about the same time to run on a 4-machine A3 cluster. And as I increased my core size, I had a good speed up of my execution time, so it went down.
How many digits are you classifying?
Sorry?
How many digits are you classifying in this example?
In this case, I don't remember, to be honest, but it's the entire data set in Kaggle, so it's
60,000?
Yeah, I think the training set is 50 or 40,000, and the actual digits to be classified are about 20, 30,000. I'm not sure. I guess I could find out. But, I mean, anyway, so it's in the order of tens of thousands. So moving on to our final example, this is actually a work that we at Nessos did with a client in Greece. This is a company called Propulsion Analytics, and what they do is they perform ship engine simulations, and they actually use these simulations to estimate performance of ship engines and diagnose engine faults. They actually approached us because they have a problem, and that problem is that the core simulations are performed using really old code, and actually this code is Fortran based. It actually spawns an entire UI every time you run it. It's command line based and single threaded, obviously, so it doesn't really utilize multi-core capacity. And up until now, they were actually using batch files and actual manual labor to run the simulations. And also, one of the problems is that the simulation code was really difficult to modify. Also, each execution of the old code could take one file per execution, and also output one file per execution. And to perform an actual simulation of an entire ship engine, it took about 1 million files to perform this. So it's definitely something that has been a problem. So they approached us, and we offered them a solution to scale out the simulation using MBrace, but still keeping their legacy code. So we would deploy this across worker roles on an Azure cluster. We would just install it using MBrace itself, store input data and output files in blob storage, and obviously also utilize the multi-core capacity of each of the machines in Azure. And all this was done in 200 lines of F-sharp code.
And you also brought in their Fortran code, or did you rewrite that?
No, we didn't rewrite a single line. They just gave us a zip file with the executable and all the resources that they use, and we just installed it across Azure.
So it's a distributed batch?
Yeah, exactly. Distributed batch, that's a good word. So for this benchmark that I ran, we tested it with about 1,000 input files, which is about 1,000th of the actual input files that are needed to perform the full simulation. Each file is about 10K, and it takes about 20 seconds to process. We deployed it again in MBrace.azure using A3 workers. Again, similar sizes as before. And again, the input size was constant across cluster sizes. And again, we had some really nice performance improvements as we increased the cluster size. So I mean, we're really happy. I mean, we're actually able to scale out without even changing a line of their data specific, like their science specific logics. Yeah.
What's the shape of that curve? It's probably not exactly halving every time.
Sorry?
Are you getting exactly half the running time every time, or is it?
So the
a little bit
methodology I
less?
used for performing these benchmarks, I actually did them a few days before flying to the US. So I used them of the methodology of just running each computation once and keeping note of that specific result. So obviously I could have, run it many times and taken averages, but I didn't do that.
The reason I ask is
Oh.
I've done the same thing. Like I scaled up over many more cores and all that, and I never got like a doubling every time I doubled number of cores. I got a little bit less. Sometimes,
Yeah,
like,
well, it's not
1.5.
exactly double, obviously. I mean, there are variations, obviously. But also, I mean, this is a really specific problem. I mean, we can easily scale out because each of the inputs are mutually independent.
Right.
So, I mean, it's not like word count. I mean, you don't really have to sort of aggregate anything in the end. I mean, you just read an input file, write an input file, you're done.
Mhm.
That's it. So, yeah, I mean, I see no reason why this shouldn't happen in this case.
Mhm.
So moving on to the actual state of the project, MBrace. It was open sourced about a year ago. Before that, it was closed source and solely developed by Nessos. Actually, I did a presentation on MBrace in New York City exactly 1 year ago, and it's literally a different code base. So it's been completely rewritten. It's a very different beast now. It used to be like a monolithic single runtime implementation on premises, etc., etc. Now it's a different thing. It's a runtime agnostic generalization of Async. It's no longer exclusively maintained by Nessos. We are preparing for our 1.0 release. We're currently in beta. We're just ironing out a few outstanding issues and writing documentation, and 1.0 should be out the gates within this month, basically. This gives you an overview of the MBrace stack. At the center of everything lies MBrace.core. It actually should have been at the top, but I've actually stolen these slides from a Spark talk that used exactly the same layout, and I sort of understood that we're doing the same thing by sort of seeing that they have the same layout. So at the center lies MBrace.core that has no other dependencies. It's it runs on its own. On top, you have libraries that run on top of MBrace core and they do not have any dependencies on the underlying runtimes. We have MBrace.c#, which is like C# friendly wrappers for all the computation expression APIs that MBrace.core offers. we have MBrace.flow, we have the hypothetical MBrace.ml, which actually doesn't exist yet. We could have many things here. Then we have MBrace.runtime core, which offers like the common framework for actually defining all the assembly distribution, REPL integration, client objects, execution semantics, fault tolerance semantics, etc., etc. And finally, we have the actual concrete implementations, which are actually pretty small projects. We have MBrace.thespian, MBrace.azure, and we actually have MBrace.aws in the works. To give you sort of an overview of the sizes of the projects in terms of lines of code, obviously the largest one is MBrace.runtime core. We have MBrace.core, which is, sorry, that's about 9,000 lines of code, all FsPickler. MBrace.core, which follows, MBrace.flow, which is a relatively small project. Our test suites that are abstract and can also be used to test any other runtime implementation. And thespian, which is a mere 3,000 lines of code, and MBrace.azure, which is just 6,000 lines of code. So these are small projects. These are really small projects, but they're also like production ready, particularly MBrace.azure. And to show you a few key people that are involved in the project, excluding myself, we have Nick Paladinos, who's my colleague at Nessos and the originator of the project. We have Kostas Rodogiannis, who is also at Nessos, and he's the key contributor for MBrace.azure. We have Isaac Abraham, who's our London-based contributor and also Azure expert. And our most recent addition is Jan Chui, aka the Burning Monk. He's a very prolific member of the FsPickler community, and he just started work on MBrace.aws bindings. And finally, we have Don Syme, actually. Don Syme, who is, in case you don't know, he's the creator of the FsPickler language. He has actually now started contributing code to MBrace. And I guess you can actually see that here. I mean, he's actually making commits all the time. Really happy about that. So this is actually a call to get people involved in the open source development. If you want to know ways of how you could contribute, there are many actually. You could author MBrace libraries. So I mean, MBrace.machine learning is a hypothetical library. It needn't be that way. There could also be graph processing libraries. There could be all sorts of libraries. I mean, and all those we are really confident that the core programming model is strong enough to express any possible distributed computation. Another line of business would be to contribute the implementation of an MBrace runtime. So you could maybe implement something that targets Mesos, something that targets Google Cloud, something that create Docker containers, your own, or even your own infrastructure, your own private infrastructure. I mean, if you want to sort of have MBrace running locally in your own data center, do get in touch. We're also looking for, primarily C# developers that might be willing to sort of offer advice on how to make better bindings for C#. And obviously something that, always pains us, documentation. It's something that is always lacking, always needs improvement, and we always look for outsiders to sort of point out deficiencies. So that's it. Do visit our website, mbrace.net, or follow MBrace the Cloud, and that's it. Thank you very much.